to the second part of section 4.2. Today we're going to solve second order linear homogeneous differential equations with constant coefficients. That's a mouthful, but essentially those are equations that look like this. And we know from experience in chapter 1 that likely solutions are of the form e to the rt. Now, if we assume that and we go through some simple calculations, which you can see here, we end up requiring that this equation is 0. This equation is 0 if and only if this equation is 0. That's called the characteristic equation. And so the way you get the characteristic equation, over here I have the equation we're solving and how to get the characteristic equation. You can see that you just replace the derivatives of y with the corresponding powers of r. So the a y double prime morphs into ar squared, the b becomes the coefficient of r, and c becomes the coefficient of r to the 0, which is 1. All right, and when you solve a quadratic equation, there are three possibilities. Case A, two distinct real roots, r1 and r2. So in that case, the general solution is right here. C1 e to the r1t plus C2 e to the r2t. Now above that, I've written the fundamental set. And in the next couple of sections, we're not going to worry about writing down the fundamental set. We'll just write down the general solution. But when we get to later sections, we will need the fundamental set. And so I just want to mention that in this box here. All right, case B is you have a repeat real root. And so in this case, your general solution looks like this. You take C1 e to the RT and then C2t e to the RT. And I want to mention all of these generalize. Like in case A, if you're solving a third order differential equation, you'll have three distinct roots and your general solution will have three terms. All right, case C, we will deal with in the next section. That's complex roots. All right, so let's just jump into some examples. Find the general solution of y double prime plus 8y prime plus 15y equals 0. The characteristic equation is r squared plus 8r plus 15 equals 0. Now, I do need the equals 0 there because this is an equation. All right, now we're going to factor that to get the roots. So the factors as r plus 3, r plus 5 equals 0. So our roots are -3 and -5. So according to the chart on the previous page, our general solution is y equals c1 e to the -3t plus c2 e to the -5t. Now the order doesn't matter. If you want to put e to the -5t first and then e to the -3t, that's fine. Okay, next one. Characteristic equation is r squared minus 2r equals 0. Let's see, factor it, and we get r times r minus 2 equals 0. So our roots are 0 and 2. So the general solution is y equal c1 e to the 0t. So I'm not going to write down e to the 0t because it's 1. So c1 plus c2 e to the 2t. Okay, next one. The next one is an IVP. So let's first solve the general solution. So our characteristic equation is r squared plus 2r plus 1 equals 0. That factors as r plus 1 quantity squared equals 0. So we have a repeat real root. R equals -1, -1. So according to the chart on the previous page, this is case B, y equals, this is our general solution, c1 e to the -t plus c2t e to the -t. All right, now we're going to solve the IVP given by these conditions. So I'm going to need y prime. That's -c1 e to the -t. And then I need the product rule. So that'll give me c2 e to the -t minus c2t e to the -t. All right, I'll call this equation 1 and this equation 2. When I put my initial conditions into equations 1 and 2, equation 1 becomes 1 equals c1, and equation 2 becomes 2 equals -c1 plus c2. So if C1 is 1, I can just plug that into the second equation, and this gives me C2 is 3. So my specific solution to the initial value problem is y equals e to the negative t plus 3t e to the negative t. Piece of cake. Okay, next one, our characteristic equation is 6r squared plus r minus 2 equals 0. All right, we can factor that a number of ways. We can guess and check, use quadratic formula, or do factoring by grouping. I've got some videos here if you want to review those techniques. I'm going to do grouping. So in this case, my AC coefficients of r squared and the constant coefficient, AC is negative 12, B is 1. I'm looking for two numbers whose product is negative 12 and whose sum is 1. So that would be 4 and negative 3. And so I can rewrite this equation as 6r squared plus 4r minus 3r minus 2 equals 0 and factor by grouping. Pull a 2r out of the first two terms, 3r plus 2. Pull a minus out of the second two terms, 3r plus 2 equals 0. Pull the 3r plus 2 out, and what's left is 2r minus 1. That equals 0. And so the roots are r equal a half and negative 2/3. So my general solution is y equals c1 e to the 1/2 t plus c2 e to the negative 2/3 t. All right, so let's look at some higher order examples. I've done the grunt work for us. So in this first one, we've got this third order linear differential equation with constant coefficients. And I went ahead and found the characteristic equation. Notice that it follows the format of finding the characteristic equation of a second order. The coefficient of y triple prime is 1, and so that becomes the coefficient of r cubed. Coefficient of y double prime is negative 6, so that's the coefficient of r squared, and so on and so forth. Then I went ahead and factored that by grouping, and you should verify that you can actually factor that. So our roots are 1, negative 1, and 6. So there's 3 distinct real roots. So here's the format of the solution. C1 e to the t, and then C2 e to the negative t, and then we just add on a third term, C3 e to the 6t. Okay, next one, another third order, went ahead and found the characteristic equation and factored it, and I see that I've got a triple repeat root. Now, if it were a double repeat root, my general solution would be C1 e to the negative t plus C2 t e to the negative t. And now, since I've got a triple repeat root, I just add on a C3 t squared e to the negative t. All right, and then the next one, I've got a combo. So I went ahead and factored my characteristic equation. I've got 2 real roots that are repeat and 1 distinct root. So again, my answer will have 3 terms, and I'll have 1 term for the negative 1. That'll be C1 e to the negative t. And then for the 2's, I'll have C2 e to the 2t, and it's a repeat root, so C3t e to the 2t. Okay, so let's do an example. Find the general solution of this third order linear homogeneous differential equation with constant coefficients. All right, so the characteristic equation is r cubed plus 2r squared minus 4r minus 8 equals 0. You should pause the video and make sure you can factor that. Okay, hopefully you did that. Let's pull out an r squared from the first 2 terms, r plus 2. Pull out a negative 4 from the second 2 terms, and we have r plus 2. This equals 0. Take that r plus 2, pull it out front, and write down what's left. What's left is r squared minus 4. Now, r squared minus 4 factors as r plus 2, r minus 2. So this is going to be r plus 2 quantity squared times r minus 2. That's fully factored. So in terms of our roots, we have r equal 2, and then negative 2 is a repeat root. So the general solution will be y equals c1 e to the 2t plus c2 e to the negative 2t plus c3t e to the negative 2t. Okay, what about when factoring by grouping fails? In this case, you can use a special case of the rational root theorem, namely, if r is an integer root of this third order polynomial, then r has to be a divisor of c. So let's see how that works in practice. Let's write down our characteristic equation, r cubed minus 7r squared plus 7r plus 15 equals 0. Factoring by grouping isn't going to work for this. So possible integer roots are possible roots have to divide the constant term. That's 15. So divisors of 15 are plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. I always start with the smaller numbers first. So we're just going to try these numbers and see which one is a root, if any. So let's try r equal 1. So plug it into the left-hand side of this equation, and the left-hand side turns out to be 16. 16 is not equal to 0, so no, that's not a root. Let's try r equal negative 1. Left-hand side, you can verify that is 0. So yes, we have a root. So what does that mean? It means that r minus negative 1 equal r plus 1 is a factor of the cubic polynomial. I'll just call it cubic so I don't have to write the whole thing down again. Now, where the heck did that come from? Well, that comes from another theorem, and I'll just state it briefly. It says that if a is a root of p of t, then t minus a is a factor of p of t. Okay, so what do we do now? We do long division. We need to take r plus 1 and divide it into r cubed minus 7r squared plus 7r plus 15. So r plus 1 goes into r cubed minus 7r squared plus 7r plus 15. Now you should pause the video and make sure you can do that long division. And when you come back, I'll have the whole answer written down, so you don't have to sit there and watch me do every step. Okay, so I hope you did that. Here's the computation for the division, and you can pause the video if you want and write that down. But what that means when you do that computation, it means that your original polynomial factors as r plus 1 times r squared minus 8r plus 15. Now, we can factor that further. We can factor that quadratic very easily by inspection. And so now we see our roots are r equal negative 1, 3, and 5. So we're in the case of 3 distinct real roots, and we can go from there. Y equals c1 e to the negative t, and again, the order does not matter, plus c2 e to the 3t plus c3 e to the 5t. And if you find in your homework that the order does matter, please let me know, and I'll let the whole class know. Okay, and that is the end of this section.